All right, so we go to the next part of this session, which is harnessing power of geophysics in entire life cycle of tunnels. So, in the very, very famous words of Shri Visvesvaraya, he said the engineer's first problem in any design situation is to discover what the problem really is. So, whenever we are doing any design, if we understand our subsurface in a complete manner, then of course our design becomes that much effective. And for that, we do investigations. So, investigations can be defined as a methodology of acquiring advanced knowledge of the site condition so that a techno commercially viable project layout can be developed. It is also a very well known fact that good quality of investigation, good quantity of investigation, and adequate time allowed for investigation leads to less uncertainties and less cost and claims, because we are very well aware of having a lot of delays in the project, a lot of claims in the project, because the geology which was encountered was not the geology that was expected. Now, this is a figure which is from ITA, International Tunneling Association, which says that even a comprehensive exploration program recovers a relatively minuscule drill core volume that is less than 0.0005% of the future excavated volume of the tunnel. Look at the figure here, 0.0005%. So this is the kind of information we are having, based on which we are doing our entire design. And very important point to be noted here is that it says even a comprehensive exploration program. When we are talking of a comprehensive exploration program, we are talking of spending something around 5% of the project cost on investigation. In India, we are spending close to 0.75% on an average of the project cost on investigations. That means in the way we are doing investigation, we can add one more zero to this. It will become 0.00005% of the future excavated volume of the tunnel. So we are working with very, very limited information when we are doing our design. And with that limited information, we definitely cannot call ourselves a smart decision maker. We are practically designing the entire thing with almost our eyes closed. And then we encounter what we call a geological surprise. So in civil engineering world or in the construction world, the geological surprise is a very well-known term. Whenever we are doing a project and we come across a geological situation, like for example, a shear zone or a fault or a fracture or anything which hampers our progress or which creates issues for our project, we came across a geological surprise. Fact is that expertise and engineering solutions are available for dealing with almost any ground condition. So, for example, you're doing a tunnel and you know that X meters from here, you're going to encounter a shear zone. So you'll just stop before that, you'll do pre-grouting and you will consolidate that shear zone and then you'll go across it, right? So the problem is meeting the unexpected and uncertainty of the ground condition. So a geological surprise is nothing but a condition which we did not anticipate because we did not adequately investigate. So the next question is, then how much should we be investigating? Should we be actually doing drilling every 10 meters, every 1 meter? Like, should we actually uh, doing drilling practically continuously? Now, that's not possible. That's not economically viable. That's not feasible. We cannot convert the ground into Swiss cheese, as we call it. And then we have to look for what is the solution. And in this case, the solution again comes in terms of geophysical investigations. Now, as I mentioned in my last presentation on dam safety also, geophysical investigations, I always correlate with medical imaging. We are sending different kind of rays and waves inside the human body to create an image of what's inside the human body. And same thing we are doing in case of geophysical investigation, where we are sending different kind of rays and waves inside the earth, or we are measuring naturally occurring fields like magnetic field, gravity field, etc., to create an image of what's inside the earth. For example, here, this is a shear zone which has been detected along a proposed dam axis. This is all rock. Here again are reinforcement bars in a concrete slab. This is the bottom of the slab. There are a few buried pipes which have been detected under various layers of road using GPR. This is electrical resistivity imaging. This is GPR. This is seismic refraction tomography, where this is a rock, and we have found out what is the elevation of rock and what is the topography of rock. This is again refraction microtremor. So in geophysics also we are doing the same thing, sending different kind of rays and waves inside the earth to find out what's inside. Our life is slightly more difficult than medical imaging professional, for the simple reason that the earth is not as predictable as the human body. For example, here we know that these are not fractures, these are joints, and they will never be interpreted as fractures. Whereas in case of earth changes every tens of meters, so interpretation of data is more difficult. Secondly, human body is available for inspection in 360-degree. You can have transmitters and receivers all around the human body, whereas in case of earth, mostly we are working with one surface which is available to us. So slightly more complicated, but fine. But then why use geophysics? There are big reasons for that. First of all, low cost. Again, the difference is the same as ultrasound and surgery. So it is a much low cost compared to expensive and extensive drilling. Rapid coverage. These days, using heliborne methods, you can practically cover hundreds and thousands of kilometers in a single day. So it's very fast to apply. Continuous information. This is the biggest point which needs to be considered. Look at this small diagram here. You have a void, and you have void here. You have a limestone pinnacle. You have various anthropological features. Now, if you are trying to investigate this ground only by drilling, what are the chances that you'll be able to map all these objects? Chances of 1 in 1,000 or 1 in million, depending on what is the spacing between your drill holes and what is the size of these objects. Whereas if you do a good geophysical campaign, you'll be able to map all these objects continuously. And then, next point, optimization of drill holes. We never say that geophysics is replacing drilling. Geophysics ultimately is giving you certain physical parameters. It can be velocity, it can be resistivity, it can be conductivity, it can be density, magnetic susceptibility, whatever it is. But it is giving you certain physical properties. There are certain physical properties which needs to be measured on core samples. Okay. Then certain verification and calibration of geophysical data also is required to convert this physical model into a geological model. So drilling is required, but what geophysics does it helps you optimize your drill holes. So instead of the current practice that we will do drilling, let's say every 400 meters or 500 meters or every 100 meters randomly, and miss all the anomalies which might be there in between, the right approach is to do a good geophysical campaign and then optimize your drilling and do drilling only at the points where you need to confirm certain anomalies, or you need to calibrate your geophysical data to convert it from a physical model to a geological model. Okay, so optimization of drill hole is the biggest point which it does. So your drilling can come down from, let's say, 100 drill holes to maybe 5, and your information will now be 100-fold because you have continuous information. And of course, this once you have the continuous information, it leads to minimization of surprises. Because once you already know that you are going to encounter, let's say, a shear zone or a bad zone, where is the surprise? So minimization of surprises. And it's always good at the early stage of application so that you can better plan your project and smoothly execute your project. Now, coming to tunnels or underground project site investigations, the method which I'm going to talk here are applicable for any infrastructure project. Although here I'm talking more of tunnels because that's really a thrust area today in the country. But these methods are applicable practically for any infrastructure projects. So once we talk of tunnel and underground project site investigation, first of all, we need to understand where does it fit in? Where does geophysics fit in? So you obviously start with available geological maps, study of the satellite images to see lineaments and all that. And then you start with geological mapping and geophysical investigations. Okay, so that's where it fits in the sequence. Always before drilling. You know, Doing drilling simultaneously or doing drilling before geophysics is like doing surgery before doing an ultrasound. Okay. So you first do an ultrasound, or you first do an MRI, or first do an X-ray to understand where surgery has to be performed. So first you do a good geophysical campaign and then do a targeted drilling there, again with geophysical logging. So you get maximum value out of your drilling also. And then hydrogeological studies, seismicity studies, etc., etc. So that's where it fits in the entire sequence. Now, coming to various stages of tunneling, we'll start right from the planning stage, we'll go to execution stage, and we will go to QC stage of the tunnel. So let's start at various stages, the planning stages. So first is fixing the alignment of your tunnel. You have to connect point A to point B, and now you have to decide how it should go. So for that, a very effective method is Heliborn time domain electromagnetic, which can have a depth of investigation of 600 to 800 meters. So this is something which can be done even in the heavily forested areas. You do not have any problem because we are working with electromagnetic waves here, so you do not have any problem in forested areas. If you look at Himalayan terrains where tunneling is happening a lot, people cannot even reach these areas, and they are densely forested. So even if you reach there, you will not be able to see any exposure to do a good geological mapping. So that's where this comes in picture. So you have to go from point A to point B, and there can be various alternative routes. So instead of just investigating, let's say, one line, you investigate a complete area in this. Okay. And here, ultimately, it is based on principle of electromagnetic. So we are sending this electromagnetic waves inside the ground. They are interacting with the subsurface. Depending on the conductivity, response is being generated, which again is picked up by the loop. So this is a helicopter. This is the EM loop, which is being suspended. And once you complete this data acquisition and processing, you practically have a 3D cube of your subsurface in the area. So let's say you have a tunnel of 10 kilometers. So you decide that, okay, I'll investigate a strip of 500 meter on either side. So you investigate a strip of, let's say, 1 kilometers by 10 kilometers. And then you have the complete 3D cube in terms of conductivity. And you will know at what depth my conductivity is decreasing. Decreased conductivity, of course, will be linked to zones which are fragile, which are problematic, which can be problematic for your tunneling. So this is a very interesting example of how it does value addition. So this is one particular client, and in this particular case, there were various possibilities of tunnel. And once the AEM was done, it was discovered that their planned route of tunnel was going above the rock level at couple of places, and this is where they would have got into problem if this investigation was not done. So based on the investigation, the tunnel route was shifted slightly to cross through the favorable geological strata. And the client says that thanks to this technique, we avoided $25 million in cost increase. $25 million in cost increase. So that is the kind of value these kind of investigation can add to the project. Ultimately, once you have done a good investigation, you have 3D volume. You can cut your slices at any point any point. And if you take a slice like this, and let's say 400 meter was your tunnel route, so if you draw this line, now you know very clearly that, okay, you're going to meet a small geological unfavorable condition here, geological unfavorable condition here, geological unfavorable condition here, and in this particular patch, the entire thing is going to be geologically unfavorable. So now before you start your execution, you know exactly what is going to be your condition as you go through the execution. And that's what avoids what we call geological surprises. So this is a very effective method if we are looking for something around 600 to 800 meters depth of investigation. Second method, which is very interesting for very high overburden areas, because sometimes tunnels are going, with overburden of even 2 kilometers and 2.5 kilometers. In that case, passive seismic tomography. Passive seismic tomography is a very interesting method which is being used a lot for oil and gas exploration at present in the country itself. It also can be used for tunnel route investigation. In this, what we are doing is we are listening to these micro earthquakes which are happening under the ground all the time. Micro earthquakes. We are talking of very small amplitude, less than even 3. And then we are recording these using these 3 component sensors. We call it passive because we are not creating any vibration artificially. We are not using any explosive. We are not putting any hammer. We are just listening to these micro earthquakes. And after listening to them for a period of time, we take this data. And based on that, we can make VP and VP upon VS model. So one gives you structural information, the other gives you lithological information. We can also do passive seismic interferometry, which practically gives you the same information like it will give in seismic reflection. And you get, let's say, this P wave velocity model like this. And here you can see the low velocity zones clearly in the subsurface. Here the depth is 2.4 kilometers. Okay. So this is a very interesting method for high overburden areas. Then we have seismic refraction tomography, which can have a depth of investigation of around 100 meters. In this, again, we are creating the elastic waves on the surface using explosive or using hammer or weight drop. And using the principle of seismic refraction, we are creating a subsurface image. Now, this is a very good case study where a geological model based on boreholes. And you can see a few boreholes were done here, and based on that, this geological model was created. Here, all this area looks to be very good rock. So this was a tunnel alignment, and as per this, except the initial part and the end part, the tunnel is going through very good rock all over. There is going to be no problem. But once the seismic refraction tomography was conducted here, you can see very clearly that here you have one low velocity zone here along the route, another zone here, another zone here. So these 3 low velocity zones are additional to whatever is happening close to the surface. And this was not detected. These zones, of course, were not detected from the drilling itself. So if you had not done seismic refraction tomography here, obviously these zones would have been discovered at the time of tunneling, and then they would have come as a geological surprise. Of course, setting back your project for a time, and then costs and claims, etc., etc. So that is the importance of seismic refraction tomography to give you a continuous image all along your tunnel route. Then electrical resistivity imaging and tomography, which can have a depth of investigation of 200 to 300 meters. Why so many methods? Very, very important thing to understand. Just like in medical imaging, we have X-ray, we have ultrasound, we have CT scan, we have MRI, depending on what is the objective. Similarly, when we are looking at the strength of the material, we are going for seismic methods. When we are looking for resistivity and conductivity, that is the water content or moisture content, etc., we are going for electrical methods. So electrical resistivity imaging and tomography is again a very strong method, which can have a depth of investigation of 200 to 300 meters, even more. And it gives you a complete picture of your subsurface in terms of 2D or 3D resistivity. Now, this is a very good case where this was a tunnel alignment. Electrical resistivity survey has been done, and 2 zones come clearly as the low resistivity zone. One is here and one zone is here. And now, based on this, and you can see this is 1500 to around 2000, so it's a long stretch of ground. Based on these zones, now the drilling has been done. So this is the optimized targeted drilling for this particular zone, optimized targeted drilling for this particular zone. So this is the concept of how you can use geophysics to optimize your drilling. You need not drill in these areas. Of course, these areas are very, very well and clearly good areas. There is no need for any drilling. If you go for random drilling, you'll be wasting a lot of time drilling all over the area, and you might end up missing these zones because they are not very thick, right? So your one drill might come here, one drill might come here, and you might actually miss these zones. But once you do this, you are able to focus and optimize on the zones which really need to be investigated by drilling. Then refraction microtremor and MASW, again, very useful for finding out shear wave velocities in the subsurface. This is an example of shear wave velocity up to 100 meters. This is based on refraction microtremor. Okay. Another method which is very important for tunnel routes or underground projects, for example, powerhouse caverns and all that, is seismic tomography, which is done between boreholes. So it is done between boreholes, and here the depth can be 100 meters, 300 meters. It is limited by the borehole depth. Equipment can be made depending on whatever depth you want to go, but it is limited by the borehole depth. So this is one of the deepest tomography, at least reported to the best of my knowledge in the world, which we performed somewhere in Bhutan. Here the whole depth was around 250 meters, and it was to map a cavity which had developed because of certain collapse in one part of the tunnel. And you can see this is the of course, this is the overburden. This entire thing is the overburden. Here is the rock, and here is the signature of the cavity. Similarly, here, these are signatures of the cavity. Okay. So very nicely it maps the cavity. Of course, it has very high resolution because we are working right at that depth. Surface methods, as they are going deeper and deeper, obviously resolution is getting weaker. But here we are working right at that depth, so resolution is very high. Seismic reflection is another method which is useful for tunnel route studies, but there are logistic issues in this. That is, you have to go all along your tunnel alignment, drill every 10 meters or 20 meters, and then use explosives to go up to that depth which you want to achieve. This is a method which is very popular in oil and gas industry, but unfortunately, when it comes to tunnel, because of logistic issues, it has not been used anywhere to the best of my knowledge. It has a depth of investigation which can be pretty large, but the problem is the logistics. Okay, it gives you the reflectors in the subsurface. Now, this method is what we are trying to achieve using passive seismic interferometry. So there we are getting the similar kind of results as we get in seismic reflection. So that's why passive seismic actually becomes very important. Then there are other applicable methods like magnetotelluric, GPR, etc., which we are not discussing here. Now, once we have done the initial studies in the planning stage, then now comes the execution stage. That is, you are now going and making the tunnel. Now, there, of course, you have a great opportunity to look ahead of your tunnel phase, because here the resolution will be very high because you are working right inside the tunnel. There are two methods which are very important. One is tunnel seismic prediction, in which we are sending seismic waves from the tunnel, and these are getting reflected from whatever are the weak zones ahead of the tunnel, and that's how we are trying to find out if we are going to come across a bad zone in front of the tunnel face. Second method is beam, which is the electrical methods. So TSP is a seismic method, beam is an electrical method, which is bore tunneling electrical ahead monitoring, in which we are making the TBM face itself as one electrode. Second electrode goes to the shield, and third electrode goes out into the ground. And now, as your TBM is progressing, stroke by stroke, you are getting information of a zone which is 3 times ahead of your tunnel diameter. So let's say you are having a tunnel diameter of 6.67 meters. So 20 meters ahead, what is the formation you are going to encounter? You will be doing continuously. You don't need to stop your operation in this particular case. The operation continues, and you will know about the presence of cavities, etc. So very, very strong method, especially for TBM tunneling. And then there are other applicable methods like GPR. You can use GPR on the tunnel face to see what's behind the tunnel face. And the last part is QC and maintenance stage. You have completed your tunnel, you have made your tunnel, and now you want to understand how whether everything is fine, whether the concrete lining is directly in touch with where it should be, whether there is any gap in between, which can ultimately lead to spalling of concrete because of delamination, etc. So there you have again GPR, which comes in very handy, which can be used very quickly to completely look at all your tunnel lining. You can convert the results into 3D. So this is a tunnel, and you are seeing inside the tunnel lining, and if there are any defect zones, you are able to see them very clearly. These are the case studies from tunnels from India only, how the defect zone is progressing. These are the slices, as if you're cutting the slices all along the tunnel length. And sometimes you have things like tunnel seepage. Now, in this case, also you can do ERI to find out exactly. So these are electrodes which have been put, and then the seepage was actually coming out from here. The common sense says that we will start grouting here, but in this area, the entire formation is very competent, very compact. No grout will go there. Actually, the bad zone was here and the seepage was taking a path like this. So you know that this is where the treatment has to be done. So this is another ERI is another very good method to see behind your completed tunnel for any such zones. Limitations and reasons for failure. First of all, inadequate planning and survey design. Your survey design has to be very good. Wrong tool selection, method lacking desired resolution, geology ignored, only single tool used. This is one of the biggest mistake practitioner can make. Two different formations can have one physical property which is the same. And that's why it's very important to use multiple tools to uniquely classify your subsurface. Then technological failures and data processing and interpretation errors. So to conclude this session, engineering geophysics provides valuable and continuous information for the planning and execution of tunnel and underground projects. The application of geophysical methods, in addition to usually applied geological and geotechnical exploration, is necessary to achieve accurate and continuous models of the subsurface in a short time schedule. To achieve optimum benefits from geophysical investigations, it is necessary to apply these methods after intensive discussion between geologists, engineers, and geophysicists at an early stage of the project. The combination of different methods, geophysics, geology, and geotechnics, as well as so-called joint interpretation techniques, will be of essential importance. Passive seismic methods are extremely effective for investigation in high overburden areas, and ultimately it leads to increased safety and decreased risk. So with this, I'll come to the conclusion of this particular session. And this is a small QR code. If you scan this QR code with your scanner, you will receive guidelines on geophysical investigation of tunnels, which has been authored by me in your email within few seconds. Thank you very much for your attention.